Another thing to notice about the periodic table that's incredibly important is that there are lots of numbers in each little box. Again, each box represents an element, a type of atom. There's lots of stuff going on. So let's look at iron for an example. Iron is here, number 26. And let's talk about different properties. We are definitely not going to use all of these. There's really just, I think, 4 things I want you to pay attention to. First of all, every element has a name, as you know. This is iron. Every element has a chemical symbol, which is like its little abbreviation. Some of these don't make sense, like iron is Fe. That's because it comes from another language, like this comes from the ancient Latin ferrous, which means iron. So it has a name, a chemical symbol, and then there are 2 numbers that are going to be incredibly important for our purposes. This number right here, which is the atomic number, and this number right here, which is the atomic mass. And really, it is the average atomic mass. So let's define what those are. The atomic number, which is sometimes abbreviated with a Z, is very simply the number of protons in the nucleus of an atom. Sometimes it's referred to as the nuclear charge. Remember, what is a proton? A proton is a positively charged subatomic particle that's found in the nucleus of an atom. It has a positive charge. What other particle is found in the nucleus of the atom? The neutrons, right? So the protons and the neutrons are found in the nucleus. The protons are charged, the neutrons are not. So the number of protons here, this is 2 protons. We would also call that the nuclear charge. So for this, Z equals 2. The atomic number is 2. This number is incredibly important because that's where each element gets its identity. So that's what it is to be an element. It's to have a specific number of protons. Every hydrogen atom is hydrogen, is identified as hydrogen because it has 1 proton. Here, this element has 2 protons. I wonder what it would be. Well, let's look at the table. Hydrogen's number 1. The atomic number 2 is right here. That's helium. So helium always has 2 protons. Iron always has 26 protons in its nucleus. That is how elements get their identity. Notice the table is organized based on atomic number, reading from left to right and then down. 1, 2, lithium is 3, beryllium 4, over, all the way to neon is 10. Sodium would then have 11 protons in its nucleus, so on and so forth. That number is also helpful for another reason, because typically speaking, that number will also be the number of electrons in the atom. So atoms tend to be electrically neutral, which means their overall total charge is 0. So what contributes a positive charge? The protons. What contributes a negative charge? The electrons. So the number of protons, typically speaking, the number of protons will equal the number of electrons. We're going to change that later and see that atoms can change their number of electrons, but for now, the number of protons in a neutral atom is going to equal the number of electrons because atoms sometimes prefer to be neutral. So that's the atomic number. The other number that showed up on the table right here is the atomic mass, or what I'm going to refer to as the average atomic mass. So for iron, it's 55.845. That is the mass in AMU of an average atom of the element. So your average everyday iron atom has a mass of 55.85 AMU. Now, why am I saying average? Why am I saying your everyday average iron atom? Because it turns out that even though all iron atoms have 26 protons, they can have differing numbers of neutrons, which will make their mass be different. Remember, where do atoms get their mass from? Well, remember our subatomic particles. Protons have a mass of about 1. Neutrons have a mass of about 1. Electrons have a negligible mass. So all atoms will get their masses from protons and neutrons. If the number of protons determines the identity of the element, then I'm telling you that each atom of an element may have different numbers of neutrons. That's why the mass is an average. This brings up the idea of an isotope. An isotope is a form of an element that has a varied number of neutrons and therefore a varied mass. And we kind of name or label isotopes with yet a third number that we call the mass number, which is A. The mass number is equal to the number of protons plus the number of neutrons. Now think about that. Why does that make sense? Well, protons contribute what to the atom? They contribute mass. They have a mass of about 1. Neutrons also have a mass of about 1. Should we include electrons in here? Do electrons contribute mass to the atom? No, they do not. Electrons have a negligible mass. We can ignore their mass because it's so tiny. So the mass number is just the countable number of particles in a nucleus. The protons and neutrons are both found in the nucleus. That's the mass number, and we call it A. This is different from atomic mass. The atomic mass is an average of all the isotopes of an element. This will never be a fraction. The mass number will never be a fraction because you can't have a fraction of a proton or a fraction of a neutron. But the average atomic mass may be a fraction. Iron has 55.845 as its atomic mass. That is a fraction because it is a calculated average of all the different forms of iron, all the different isotopes. Let me give you some examples of isotopes. Hydrogen has 3 stable isotopes. We call them hydrogen 1, hydrogen 2, and hydrogen 3. This number that you see after the hyphen, that is the mass number. So it is the number of protons plus the number of neutrons. So let's see what I can figure out about hydrogen 1. I want to know how many protons, how many neutrons, and how many electrons hydrogen 1 has. So the number of protons, well, it's hydrogen. It gets its identity from the number of protons that it has. So let me go back to the periodic table. Hydrogen has an atomic number of 1 in the upper right corner. What does that number mean? It means the number of protons. Therefore, hydrogen 1, I know, has 1 proton. What other subatomic particle do we know right away? Well, we know that the number of electrons has got to be equal to that. So 1 proton, 1 electron. Why is that true? Because atoms are typically neutral. The protons and electrons are balanced out. The positive charges and the negative charges are balanced out. How about the number of neutrons? Can I figure out how many neutrons hydrogen 1 has in its nucleus? I could. This number right here is the mass number. The mass number is protons plus neutrons. So for hydrogen 1, the mass number is 1. The number of protons is 1. So can I use some simple quick algebra to figure out the number of neutrons? Yeah, it has 0 neutrons. This is the simplest atom that exists. 1 proton, 1 electron, that's it. No neutrons at all. How about hydrogen 2? How many protons does it have? Would it have 2 protons? No, that's not what this number means. It's hydrogen. Every hydrogen atom has the same atomic number, has the same number of protons. That is what makes it hydrogen, 1 proton. How many electrons, therefore, does it have? 1. Those are the same. How many neutrons does it have? Well, this time the mass number is 2. That's what this number means. That's going to equal the number of protons plus the number of neutrons. Number of protons is 1. The mass number is 2. Therefore, use some simple algebra. How many neutrons are there? 1 plus blank equals 2. Yeah, very simple. The answer is 1. 1 proton, 1 neutron, 1 electron. You figure out hydrogen 3 for me. Yeah, so very simply we see that the mass number is 3. That's what this means. So we know that has to equal the number of protons, which because it's hydrogen is 1, plus the number of neutrons. The number of neutrons here has got to be 2. These are isotopes of hydrogen. They are different forms of hydrogen having different numbers of neutrons and therefore different masses. The mass of hydrogen 1 is 1. The mass of hydrogen 2 is about 2. Of hydrogen 3 is about 3. Why? Because their neutrons vary. Does that mean it's no longer hydrogen if the number of neutrons varies? No, because the number of protons has remained constant. So these are isotopes. What I'm telling you is that on the periodic table, when you look at the average atomic mass, that is an average of the isotopes of that element. And it's a special type of average called a weighted average, which means it's been weighted based on the abundance of that type of isotope. So let's look at hydrogen's average atomic mass. Hydrogen has an average atomic mass of 1.008, give or take. So because its average atomic mass is about 1.008, this tells me that most of the hydrogen in the universe is hydrogen 1. How do I know that? Because this number, the average atomic mass, is a weighted average. It's the average of all the different isotopes, considering their abundance. So remember, the three isotopes of hydrogen are hydrogen 1, hydrogen 2, and hydrogen 3. Hydrogen 1 would have a mass of about 1, 2 would be about 2, 3 would be about 3 AMU. If I were just to take a simple average of these, 1 plus 2 plus 3, that's 6 divided by 3, the average there is a 2. That's not the type of average I'm talking about. It's a weighted average. It's based on the abundance of those isotopes in the universe. It turns out that most of the hydrogen in the universe is hydrogen 1. So the way this is calculated, I'm not going to have you calculate it, but the way it's calculated takes that into consideration. So this is a weighted average mass of all the isotopes of the element, considering their abundance in the universe. Here's some more examples of carbon, carbon-12 and carbon-14. Let's just see if we can determine the number of subatomic particles in these. Remember what this number is? This is the mass number, A, the mass number. That's the number of protons plus neutrons. So carbon-12. According to the periodic table, carbon has an atomic number of 6. If I look at the periodic table, there's going to be a 6 up here. That tells me what? The number of protons is equal to 6. I also know, therefore, the number of electrons is equal to 6. Can you figure out very quickly the number of neutrons? It is also 6, because this number 12 has to equal the number of protons plus the number of neutrons. The number of neutrons has got to be 6. Here for carbon-14, the protons still 6, electrons still 6. How about the neutrons? The mass number is 14. That's the number of protons plus the number of neutrons. So that has got to be an 8. There is another way of writing isotopes, another notation style, called the nuclide symbol, or the nuclear symbol. With the nuclear symbol, it's very simple. You have the chemical symbol, C, and instead of writing out the name and then putting the mass number out here after a hyphen, that's one way of talking about an isotope. It's very simple. You put the mass number in the top left and the atomic number in the bottom left. So carbon-14 would be 14 up here, and the atomic number is 6. This is helpful because you can determine the number of neutrons really easily. You just subtract these numbers. This is the mass number. That's protons plus neutrons, right? That's A, the mass number, protons plus neutrons. This is Z, which is very simply just the number of protons. So if you subtract these, what are you going to get? You're just going to get the number of neutrons. So I know very quickly that carbon-14 has 8 neutrons. Where are the neutrons found in the atom? In the nucleus. These are isotopes, different forms of the same element. These are all carbon because they all have an atomic number or a nuclear charge of 6. The Z is 6. But they have different mass numbers, different masses because they have different numbers of neutrons.